Good morning, ladies and gentlemen. So while we are working out, okay, maybe a little lower volume. So we are working out some kinks here. I can start the introductions. First of all, welcome back to campus. It's a nice day, unusually nice day. For those of you who are freshmen on spring admits, welcome to Berkeley. Any freshmen, spring admits? Great. We picked the best class to start, I think. So, yes, welcome future presidents, Nobel laureates, vice presidents, prime ministers, queens, kings, whatever. We are going to talk about physics in this class. So first of all, okay, let me introduce myself. My name is Yury Kolomensky. Obviously, you'll notice a slight Russian accent. There's a reason for that. I'll tell you a little bit about what I do when I don't teach this class. But first we'll discuss why all of us are here. I'm looking for props. So, I guess first let me tell you again about what I do in my spare time. I'm an experimental particle physicist, which means that I study in my research time the most fundamental, the tiniest, the smallest constituents of matter, and try to figure out how they behave, how they work, how they interact, and actually what makes up, how those particles, make up the universe. Somebody contacted me recently about an interview, and they were saying, well, the person was interested in nanoscience and nanotechnology. That's a popular word. It usually describes, again, behavior of matter on atomic scales, basically on the scales of atoms that compose the periodic table. Usually it means material science. It usually means applications of material science and physics to engineering. Nano, we'll talk about prefixes and suffixes. We'll talk about this. Nano means small, or 10 to the minus 9 meters in atomic scales. What I study are even things are even smaller. So kind of an inside joke is that what we are doing is femtoscience, things that the behavior of particles and matter and forces on the scales that are much smaller than atoms, on the nuclear scales and subnuclear scales. And the main reason to do it is, well, part of it is human curiosity, part of it is, I think, our contribution to society that we would like to understand ultimately where we come from, not just as a species, but as part of this cosmos, where it all is going, and fundamentally how things work, both from the point of view of applications and from the point of view of fundamental knowledge. So, what is that, perhaps? So, this is actually what we know about the universe. Particle physics is sort of this reductionist, takes this reductionist approach to answering the big questions about the cosmos. We think that so far the entire universe consists of fundamental particles of matter. They are called quarks. And so these particles are called leptons. Really, what most of the stuff is made of is this column, nuclei made of quarks, and then electrons orbiting the nuclei in the atoms. Atoms make up relatively complex structures that make up periodic table. The atoms then can assemble in molecules or crystallized structure, solids, liquids, gaseous forms of matter, and that ultimately makes up everything that we observe. Of course, in addition to that, there are stuff called antiparticles. We'll talk about this towards the end. You can ask me. We don't see these antiparticles, but we see hints that they at some point existed, and we can make them in the laboratory. So I do experiments that make particles and antiparticles in the lab, and then watch them collide with each other, annihilate in a fiery collision, and we study their properties. Ultimately, we, again, trying to figure out how these fundamental constituents of matter make up what we observe at the grander scale. So in some sense, it's trying to understand how microscopic physics defines what happens at the scales of the universe. So particle physics connects small to very large. I did mention why. Well, okay, curiosity is one thing. I think it actually, fundamental physics does have contributions to society. It really, we are trying to advance the knowledge, human knowledge, our understanding of the world as a race, as a human race. People have been curious about how the world works for as long as we remember. You know, when you were little kids, perhaps you may have looked up or you may have looked around us and you ask, why? Everybody does. You know, I had my kids are grown up now, they're in college, but when they were small, they would ask, why? Why? Why again, right? That's very natural for little kids, but also very natural for adults as well. Journal of Science actually puts this question of how does the universe work and what it is made of as one of the most interesting, most fundamental questions, perhaps of the 20th century and the 21st. But also fundamental physics, fundamental science also leads to applications, and this is where there's a complementarity between fundamental physics trying to kind of answer abstract questions and direct contribution to society comes in. Progress, engineering progress, scientific progress, technological progress is often driven by human desire to push the boundaries. And these fundamental studies require us to be at the frontier of technology, frontier of science, to push the boundaries of what is possible. And then we can figure out later often how to advance that frontier and use our understanding for good, or sometimes not so good. And again, human history is filled with examples of applications of fundamental science going back to Archimedes, who was, famously, so this is actually the picture. I don't know if you know the story, which may or may not be true, but a legend says that when the Roman fleet was trying to attack Syracuse, not Syracuse, New York, Syracuse, Greece, Archimedes developed a technique for defending the, actually now I don't remember, is it an island? I don't think it's an island, it's a city. How to defending the shores from the flammable Roman fleet. He studied optics, so he figured out that by carefully assembling mirrors on the shores and focusing sunlight onto these battleships, they can burn them. If you watch Mythbusters, and if you watch Mythbusters, right, there was an episode about this. This is not as easy as it looks in the picture, but this is one of the applications of perhaps military application of fundamental, at the time, state-of-the-art knowledge, optics. Archimedes was also quoted as saying that if you give me a point, I can turn over the world with a big enough lever. This is the example of that. As far as I know, this experiment has not been performed yet, but fundamentally it's possible. Of course, invention of lasers now, including this one, are everywhere in our lives, in your CD players, DVD players, laser pointers, and even, again, high-power military applications. Fusion, you know who invented laser? Well, probably not these guys. They're using it. Charles Townes is, in fact, a UC Berkeley professor in the physics department. He's emeritus professor, but he comes to every physics colloquium. He sits in the front row, unlike some of you. He asks questions. He developed laser in the 1950s. It was actually invisible laser at the time based on the carbon dioxide molecules, but the principle still works. Another example here is, again, the fundamental physics. This is the picture of human brain as mapped with the so-called MRI technique, which we'll talk about in this course, magnetic resonance imaging, otherwise known as nuclear magnetic resonance. There's also a story there. The way this technique works, I'll actually show you in a second. I used it in my PhD thesis experiment some 20 years ago, which again is an application of fundamental development of fundamental science, later applied to this picture, will come up, to medicine. Nuclear magnetic resonance looks at vibrations, rotations of nuclei, the tiny little magnets, they're called magnetic moments, spins of nucleus, or nuclei. They can be made to spin in a magnetic field, and the spinning creates small radio frequency vibrations of electromagnetic field, small radio waves, just like the radio waves that work with your cell phones, and that those radio waves can be detected. And then intensity of the radio waves will tell you about distribution of these little magnetic moments, distribution of matter. So this can be used for imaging, can be used for imaging blood flow in human brains. In my experiment, this was used to image distribution of these tiny particles, quarks, in the proton and the neutron. This was the object of my thesis research. We used so-called polarized, there was this little piece of glass that was filled with polarized helium-3 gas. Helium is here in the periodic table. If you look at helium, it has the atomic number 4, which means that it weighs roughly 4 times as much as the hydrogen nucleus proton. But we used a particular isotope of helium, non-radioactive isotope called helium-3, which could be made to spin in a magnetic field. And we used that to perform studies of structure of the protons and neutrons. Later on, this technique was used by the group that developed these targets. It was the group at Princeton that later the Professor Gordon Cates went to University of Virginia. And they developed this technique of using polarized noble gases to image human lungs. Here's the picture. Real-time image of using small, tiny magnetic fields produced by the nuclei of xenon, in this case, to image the airflow of human lungs. This would not be possible with the regular MRI techniques. This is only possible because of the high magnetic fields produced by this xenon gas that can be inhaled. The MRI technique really depends critically on how much magnetic field the nucleus produces. Normally, it uses protons, and there's not a lot of protons in the human lung to start with in air. So this technique is essentially a spin-off of the fundamental science that was developed about 5 years after my thesis experiment. So let's see, I had a cheat sheet here. So the question is why I understand why I would like to study physics. The question is why you're in this class. There can be several answers to that. One is that you actually have to graduate from Berkeley, and so you have to take a breadth requirement, and that includes science courses. So you look in the catalog, and you picked one. I think you made the right choice. Hopefully you agree towards the end of the semester. The main reason is that, again, you will be graduating from this great university, the greatest university in the country, in the world, or in the known universe. You'll be educated members of the society. And so you need to understand fundamental issues. And you need to understand you someday may be important. Hopefully all of you or most of you will be important someday. You'll be making decisions. We'd like to teach you how to make informed decisions. In particular, we'll tell you in this class how our fundamental understanding of the world around us, namely physics, applies to the society, applies to technology, to engineering, and to the difficult questions that may face us as a society or a species. So that if you are making decisions for the country, for the world, at some point you can make them with the solid understanding of the facts. I'll not talk about politics that much for multiple reasons. One is it can be polarizing. This also is not political science class. I have opinions. You can ask me about my opinions. I will try to be fair and balanced, as a tagline for a certain show says. I will generally stay away from the politics, but I'm happy to discuss applications or implications of technology to society. And this is also maybe a great topic to discuss in discussion sections, which, again, human understanding develops best in humans are societal creatures, so it develops best during the interactive process. You'll be split into small groups in discussion sections, and hopefully you can actually discuss both the facts and how they apply to you, or how they apply to important issues for you. The most important thing is what I would like to get out of this class is that physics, science in general, is no black magic. Well, I guess in high school or in middle school or even in elementary school, you are taught something called the scientific method, which requires postulates of some hypotheses, experimental tests, and then iterations. I really would like to impart that technique, that thought process on you. So you'll be remembering some facts from this class, but you also should learn how to apply it logically to fundamental issues that will face the human society. In particular, I'll show you some examples of how technology works. We'll discuss technology, we'll discuss weapons, so we'll discuss energy, various energy sources. And so you will hopefully understand at the basic level, at the level that will be required of the leaders of the world to understand them, to make important decisions. Of course, there are other applications of this fundamental knowledge, probably more immediate applications of this fundamental knowledge. For example, any of you have, probably many of you have to work after school. Are there any, waiters or waitresses part-time here? Maybe not. Okay, you don't have to admit. Even if you don't work in the restaurant industry, you may be, hosting a dinner party at some point, cocktail party or something. There are some cheap parlor tricks that you can demonstrate with the solid understanding of the physical principles, such as this one. Serve nice china or dinnerware, and then do something like this. This is the basic demonstration of inertia, which is one of the important physical principles that we'll talk about, I think, in week 2 or 3. Okay, this is one example. I will probably embarrass myself now. I'm a little bit rusty out of practice. There's other applications of fundamental physics, like this one. I haven't grown up in Texas, as you can tell from my accent. But I hope not to injure you. Duck, if you must. The sound that you hear is a sonic boom produced by the tip of this bullwhip. It's a little better. I'll tell you how it works in due time. So these are applications of physics principles. And hopefully, as the semester goes along, you'll see more of those. Rich Moller, who wrote the book, has this great line that physics is the liberal arts of high tech. Many of you are in the liberal arts majors, so hopefully you can relate. This is something we tell our majors, physics majors, not just non-physics majors. We basically tell them that with a physics degree, they can pretty much do anything in any high-tech field, and this is generally true. Only about half of the physics majors actually go on to physics careers in graduate school elsewhere, and the rest can be engineers, lawyers, patent clerks like Einstein, finance bankers, doctors, medical doctors, etc. There's a very broad range of careers, and physics will give you and them, hopefully, skills necessary to succeed in those fields. So, long story short, this is Rich Moller. I hope to introduce him to you personally at some point. He is a world expert on global warming. We have a topic on global warming later in the semester. I hope to invite him to actually tell you his thoughts and opinions on the matter. You have probably seen him, or you can Google and see YouTube clips of him on TV. The topic also is covered in his book. So Rich has developed this course about 10 years ago, and again, the main object of the course is to tell you, describe you the important features, the important applications of science, and besides, it's a much greater title of a course than Physics for Poets or Physics for Dummies or something like this, because you ain't no dummies, and even, some of you may be poets, but Physics for Future Presidents, I think sounds better. Okay, so there are some popular culture references. Many of physics majors have experienced this. Many of physics professionals have experienced something like this. Many of you have taken physics in high school. If you're not physics major, there's probably reasons for that. I experience this quite often. I travel a lot. One of my experiments that I do is in Italy. The other one is near Chicago at Fermilab. So, all of us at some point, professionals, experience this. You get on an airplane, it takes off, 10 minutes later you open your laptop, you have to do work while flying too, and the person sitting next to me would ask, what are you doing? You must be a computer programmer, Silicon Valley guru, whatever. I usually take this as a compliment. And then I say, no, I teach physics. And then the response usually, there are typically two responses. One is kind of a mild amusement, and they think sort of, what the hell do you actually know about physics? Oh, I heard about this Large Hadron Collider somewhere in Geneva, and that it's going to produce black holes, and they will eat up the whole Earth. Is that actually true? About 10% of the time I get that response. 90% of the time I get the response, I flunked physics in high school. That's our experience with the society. Again, my goal here would be to make you feel much more at ease with the topic. It will not be mathematical, not really, there will be numbers, but the idea of the course is to give you the important kind of high-level understanding of how things work. But again, in popular culture, there are many references, usually comedic. So here's an example. So that's the punchline. And so my job here for the next semester is to make sure that you understand it. So again, our coverage will sort of have two flavors to it. On one hand, again, and this is something that attracts me to the subject, is I said that physics is kind of the ultimate reductionist science. We condense the complicated, extremely complicated behavior of the world, not just societal human interactions, but everything that we see. We try to boil it down to a small set of fundamental laws that can be then applicable with some simplifications and perhaps approximations to a wide variety of situations. This is really what this elegance is what attracts me to the subject. And so there are techniques for studying the universe. They typically kind of behave, they sort of typically work sort of in a kind of deductive reasoning sort of way. we abstract, and we generalize. And we try to come up with a set of fundamental descriptions, fundamental laws that can be applicable to situations that may not seem, at first glance, all that related. Simple example could be that, if you're a calc quarterback, Jared Goff, right, current one, you obviously need to know how to throw. I'm not that great, but I can try. You need to hit a receiver, hopefully, 50, 70, 110 yards downstream, down the field. Nobody can do that. So you need to know ballistic motion. I can try to demonstrate, heads up. Yeah, chair caught it right. Yeah. Oh, yeah. All right. I'm a better receiver than a quarterback. Of course, the same phenomenon, the same ballistic motion applies to ballistic missiles. So the same knowledge is needed by a president of the United States when he's considering what to do with North Korea after they learn the parameters of the recent missile test. Right? You would like to know, does this missile travel 1,000 kilometers, 1,000 miles, or 10,000 miles to the shores of California? Same fundamental laws describe the behavior of both objects with some simplifications. You may or may not ignore air resistance. You may or may not consider the spinning of the ball, etc., etc. But the same fundamental set of laws can be applied to at least make orders of magnitude estimates. So, again, our goal is to tell you about a relatively finite set of fundamental laws and then tell you how they apply to everyday life, to society, to technology. So, aside from this spiel, I also want to tell you how to learn physics. If you're one of those neighbors that I've seen on an airplane who flunked physics in high school, you probably were not taught how to study it properly. Happens to all of us. This is how you should study. All of us have to learn somehow. I got this from this concept from an Air Force colonel, as it turns out. When I was effectively a freshman faculty, junior faculty here at Cal, in 2001, the physics department sent me to a teaching conference organized by American Physical Society so that I could learn how to teach. Teaching is an acquired skill as an art. So among various workshops there was a instructor at the Air Force Academy. And she said that all studies of human behavior, psychology, and just educational science tell you that there are basically 4 stages to learning, 4 steps in understanding. You start from ignorance. And then you open the book and you acquire a second state of understanding, which is actually confusion. This is very common. You open the book and it starts with Greek. Oh, literally. We use Greek symbols in physics. So things will look foreign to you. It's all Greek to me. And it will take some effort to understand the material. And generally, that effort requires reading, listening, discussing the material over and over again. Second stage in understanding is so-called consciously competency. So this is real understanding. And then only when you do this multiple times, in particular, only when you have to explain the material to somebody else, I teach or discuss things in discussion sections, then you reach the full mastery of the subject. These are the 4 fundamental steps. So what I would like to implore you is that when you come to class here, when you come to lecture, I don't want you to be ignorant, because then you leave the class confused. That's not what I want. I would like you to come to the class confused and hopefully leave with some understanding, and then you go to the discussion section and you achieve mastery of the subject. What it means is that when you come here, when you come to class at 9:30 in the morning, you should have read the materials in the chapter. You should have been prepared to ask questions. I will typically, except for today, since I had to introduce myself, I will typically pause for about 5 or 10 minutes in the beginning, and I'll have you ask questions, if you have any. Don't be afraid. Don't be shy. No question is the wrong question. And then hopefully you leave lectures with some degree of understanding, having clarified some of the confusion, and then you go on and you iterate, you do homework, you read popular articles in the various journals. That's part of the homework assignments. And then at the end of the week, hopefully you leave with profound understanding or mastery of the topics. So this is how I would like you to learn. Of course, I was told this theory by an Air Force colonel, and things usually work a little bit better in the Air Force Academy. They said 95% of our students come to the class prepared, having read the chapters because they've given the orders. Hopefully you behave this way because you would like to learn and not because you are given orders. Now, let me tell you a few words about the class organization. You have heard that Berkeley has migrated or is migrating to this new online tool called B Courses. We have migrated to B Courses. You should have received an email last night, when I activated the site. This is the URL. I will post these slides on B Courses. Of course, it won't help you if you can't log in. Most of our communication will be through that. There may be hiccups along the way, and we'll try to deal with them. Generally speaking, this system is better than, at least improved compared to BSpace. If you have any technical issues, please let me know. Please let our GSIs know. I will introduce them in a second. So let me show you this site. If I can figure out how to drag my screen. Oh, there it is. So let me go through the syllabus first. So first of all, there's information on lectures, my office hours after class. We have information about how you can get in touch with the head GSIs and other GSIs. Punit is over there on my left and your right. GSIs are your friends. Please go to the discussion section. They're here to help. Talk to them. Get your concerns ironed out with them. Use them as the greatest resource at this university. Aside from me, of course. Now, okay, no prerequisites. I'll come back to the numbers and mathematics a little bit later. An important point. This is an early drop deadline course. This room is filled not quite to capacity yet, but it may fill up. So you should decide by the end of next week, by Friday the 31st, I believe, whether you'd like to stay in this course. Hopefully you do. And either drop it or re-enroll. Are there anybody in this class on the waiting list? Not really. We have a couple of sections that are full. So there may be a few students on the waiting list. Attendance is important. In particular, attendance is important in discussion sections. We'll run the discussion sections interactively. This is where you'll be, again, discussing societal applications, hopefully, technological applications of what we learn in class. So we do require you to be in the discussion sections. Of course, life happens. We understand that. So the only requirement for missing a section and not incurring a penalty is emailing to your GSI or to the head GSI ahead of time that you're going to miss the discussion section. It's very simple. You don't have to make up an excuse. Any excuse is fine, but you have to notify us in advance. And then, so the stick in this is that if you miss 3 discussion sections, your grade may be dropped, or will be dropped by 1 grade point. So no penalty for missing 1, no penalty for missing 2, a whole point for missing 3. So there's some leniency, but this is a relatively easy requirement to satisfy. The attendance in this lecture is voluntary. I would like you to come. I think you will get more out of being here in person. Lectures are webcast, so if you have to miss a class for any reason, you can look at it online. We'll put a link on the B Courses website. You can also find it on the YouTube or iTunes channel for UC Berkeley. Now, to encourage you to come, we've invented a carrot, and this carrot is, where's my screen here? This carrot is a small amount of extra credit that you'll get. So we'll administer, starting next week, we'll administer quizzes using clickers in this course. Many of you actually have to get clickers for other courses anyway. There are two parts to grading the quizzes in lecture. You'll get 2% for just completing this quiz, and you'll get 3% more for actually answering the questions correctly, which should be relatively easy if you have read the material of the chapter ahead of time. So that's the carrot. You can get up to 5% of extra credit for being here and answering the questions correctly. So clickers, I will make a demonstration next week. So the quiz next week will not count, but we'll try to iron out the technology. And we'll use that both for audience participation. That's actually is a very good interactive tool where I can poll you either on the actual quiz, or we can discuss some more complicated topics, so I can poll the audience. Homework. There will be a weekly homework. It's due, the writing part of it is due on Monday. Part of this course, again, it's called Physics for Future Presidents. What I would like you to get out of this is being able to discuss technology, being able to discuss science well, in good English, and being able to communicate science to policymakers. So the homework is has two parts. One part is an essay that you write every week in the form of basically a brief that you can imagine writing to a congressman, senator, president, pope. So the length is about a page, 3 to 4 paragraphs. It has to be written in good English. We'll make sure that you understand how to structure. If those of you who are not native speakers like myself will eventually need to learn that as well, we'll teach you how to structure those essays. And there you can either write an essay on a predetermined topic that we'll post every week, or you can pick a topic yourself. You can read an article from an online or offline source, from a respectable source, and here are the list of respectable sources. And then you'll summarize that article, the article on science or technology, in the essay. So again, you can either answer a predetermined prompt, typically on the material of the lecture for that week, or a free prompt. I discussed that there will be quizzes in lecture, and so the second part of the homework will be a 5-question multiple choice quiz also every week, due at 9:30 each Tuesday before this class. And so the quiz online will cover the material that we will discuss that week. So again, this is to encourage you to read the material in the book ahead of time. Here are the list of the GSIs. We have, I think, 2 GSIs plus Puneet, again, sitting on the left here. You guys wave your hands. Again, one more, 4, 5. Stephanie is in the back. Again, one of the great resources of this great university are graduate students. We are very selective, especially in the physics department. We are routinely number 1 or number 2, depending on the strangeness of the poll in the country, in graduate education, graduate school in physics. Our acceptances are extremely competitive. These guys have beat out about 900 other applicants in the year that they were admitted. We accept about 100 each year, graduate students. So these are some of the best and brightest in the country. Use them as such. Ask them questions. Ask them for advice, career or otherwise. These are some of the greatest resources in this university. There will be 3 exams. There will be 2 midterms. Please notice these dates. Write them down. Check them with your schedule. You must attend them. In particular, you must attend the final. If you have any conflicts, you have to notify us, me and the head GSI Punit, ahead of time. We can, if you are traveling for any university-sponsored reasons, we can work out alternatives, but generally these exams will not be rescheduled. There's information about incomplete grades, and there's also information here. If you're new to Berkeley, this is a big place. It takes a while to get accustomed to the pace. It gets, takes a while to be accustomed to perhaps competitiveness in some of the courses. Not in this class. This class will not be cutthroat, I don't think. But public university like Berkeley has certain pressures associated with it. There are great resources available to you if you find yourself in trouble, either academically or if you find that you are having difficulty coping with pressures. Here's the link, for example, to a list of these resources, both advising and otherwise. And again, if you need to talk to me for any reason, I'm more than happy to help you if I can or point you to the appropriate resources. Communication, feel free to write me an email. Feel free to write Punit, the head GSI, an email. There will also be a Piazza forum. That's an online tool that you can use to communicate with your peers, communicate with the GSIs, or myself, ask questions about anything. And of course, I also would like you to ask questions here in class, again, about anything related to the course or anything related to science article you have read, and we'll dedicate about 10 minutes in the beginning of the class to answering those questions if you have those. So again, the best way to learn is be interactive. And of course, the last part that unfortunately we have to say is that you all have read, hopefully, the Berkeley Honor Code that bears don't cheat. There's in particular in this class, since it involves essay writing, you hopefully have learned how to write proper essays in high school, but sometimes you have to be reminded of this. It's sort of easy to get inadvertently into a mode that's somewhat suspicious or questionable. The question of plagiarism is important when you're writing. You have to make sure that you're not stealing somebody's work or you're not using somebody's work without proper citations. And again, if you have questions about how to properly reference sources so that you don't take credit for something you didn't write yourself, let us know, ask. But the policy here is clear. If you are caught, we will have to take action. So that's so far all logistical information. Do you guys have any questions about logistics? And then we'll proceed. Very good. So again, probably the most important part is for me to figure out what you guys want to get out of this class, aside from an A grade. So I would like to know what you would like to learn. You can ask me now. You can ask me later. You can ask anonymously in the forum. You can ask personally by email. Any, or in office hours, anything like this will work. So please give me feedback, give our GSIs feedback, tell us what you would like to learn. If you have any questions right now about anything that pops in your mind that's science, physics related, I'm more than happy to pause here and answer. All right. Don't be shy. So the last part, and again, this is sometimes the subject that makes physics appear difficult, is mathematics. Of course, math is the language of science, and in particular, it's the language of physical sciences. This is the way we communicate. And there's a reason. Physics is experimental science. Physics is a precision science. Experimental science means that we postulate some hypotheses, physical laws that are typically postulated in a numeric or through formulas, and then we test them numerically with high precision. It's also important in other places in the world. If you're building a bridge, you obviously have to be numeric about it. You have to know that the Bay Bridge is, what is it, about 7 miles long. Giving the length of the bridge to an order of magnitude, 10 plus or minus 2 is probably not good enough. So we describe fundamental physics laws using the language of mathematics, sometimes very complicated mathematics. Calculus is probably the easiest mathematics possible. You may have heard about string theory that involves topics that even I don't understand, like differential topology. Some of our GSIs may be working on eventually on theory. No? Nobody? No? Good. So some topics may be very mathematically complicated, but we will not do that in this class. Our goal here is to tell you basic, fundamental, most important concepts that you need to understand the world around you, and we will express numbers often. Even though the main purpose of this course is to tell you concepts, knowing numbers is often important, and so there will be a lot of numbers in this course. It's useful to know, for example, how much electricity you can collect from sunlight in the Mojave Desert. Why? Well, you may be building a plant there, and so knowing that you can collect as much as a gigawatt of electric power from roughly a square mile of area is useful to know. That sets the scale for a typical solar power plant. It's also useful to know what a gigawatt is. It's useful to know that a typical nuclear power plant, like the one in Diablo Canyon near San Luis Obispo, generates something of the same order of magnitude of power, about a gigawatt per nuclear reactor core. Numbers like this are often important to understand. There are probably more mundane applications of these numbers. For example, I'll tell you, we'll talk about sound and waves later. You know that any wave, or you understand that any wave like sound propagates with finite velocity. So if you're out on a golf course somewhere and you walk around waving metal sticks in the air, and clouds start gathering, and you see a lightning strike, and then you hear the roar of thunder a little bit later, it's sometimes useful to know how far the lightning strike is. Do you have to kind of run and hide, or can you finish the 9 holes? So there's a basic rule: if you see the strike, and then you can listen how much delay is between the light and the sound. You count Mississippis, right? 1 Mississippi, 2 Mississippi. The rule is that 5 seconds of delay is equivalent to a mile of distance. That's the speed of sound in air. So if you see a lightning and you have counted to 5 Mississippis, and so the thunder came, well, the strike is about a mile away. You have some time to figure out where to hide. If it's on you in 1 Mississippi, well, maybe you shouldn't be waiting metal sticks in the air. So, these are useful things to remember. There are other useful things or order of magnitude estimates that you can sometimes make, and skills of estimation are important in science. For example, little kids, boys, usually, flamboyant, energetic, jump from some, heights, or, if you are trying to escape from a building that's on fire, you may think, well, should I jump from a window or try to run downstairs? Knowing things like, what's the highest elevation that I can jump safely from might be important. These are things that you can estimate. I can demonstrate. There are actually many ways to estimate this. One is to write formulas. I can probably I'll try to do the formulas here. Do I have any chalk? I have a chalk. So one way to estimate what's the safest elevation that you could jump from. All right, I'll estimate it using formulas. You will not be doing this, you don't have to copy. So the way I would do this, I will say that energy is equal to mass times g times h. I won't tell you what this is. This is equal to kinetic energy, mv squared over 2. That's equal to the work done by your ankles to stop you, F delta x. So you can estimate the force on your ankles. Force is mass gh over delta x. So acceleration on your ankles is force over mass is g h over delta x. So the force on your ankles will be g times this ratio of height from which you jumped times delta x. What's delta x? That's the amount of knee bend that you made. So if you say my delta x is about 0.5 meter, the maximum height is delta x times the ratio of acceleration over g. So if you know that your ankles are designed to withstand acceleration of, say, 3 g's, then you can jump from the height of 1.5 meters or about 5 feet without fear of breaking them. And I can test this hypothesis. I actually broke my ankle at some point. Not jumping from tables. Luckily in class, I broke it playing ice hockey. So I have to be a little bit careful, but generally jumping from the height of about 3 feet is safe. I don't necessarily want to have you do this calculation every time you're jumping. You can estimate the same thing using some basic engineering scientific principles. In fact, one of the most fundamental physics principles is the fact that every action, most physical laws are reversible. Gravity is reversible. The same amount of force applied to your ankles when you're jumping down is going to be applied to your ankles when you're jumping up, trying to get to the same height. So if I were able to jump onto this table safely, I should be able to jump from this table safely. Of course, we know that white men can jump, and so therefore, nature probably haven't built me exactly to jump from this height. I can try, but it's not quite enough. But I also know that nature has built safety margins in my bones, similar to engineers building bridges, typically build safety margins of about factor of 3 to 5 in force. So if I measure how high I can elevate myself, say, I'm optimistic and maybe I can elevate myself to the elevation of, say, 2 or 3 feet, if I know the safety margin is a factor of 3 on my ankles, that means I can safely jump from the elevation of about 3 feet times 3, 9 feet. That's roughly at the borderline before you start breaking bones in your body. So again, this basic calculation, the fact that you can measure forces jumping up and then multiplying by whatever safety margin engineers have built into your equipment or nature has built into your bones, will tell you the basic ways to estimate safety in this particular situation. Well, just to conclude, we'll use some basic mathematical operations in this class. Sometimes people ask, well, should I use a scientific calculator? The answer is no. Since most of the numbers we will expect you to know are to 1 order of magnitude, that is 1 digit, you should be able to compute things like that in your head. But if you must, you can use a calculator in your smartphone, not on the exam though, or basic arithmetic calculators that can do square roots. We'll use scientific notations, however, and this is the scientific notation. So I'll post the slides on the web as well with the mnemonic for how to figure out prefixes kilo, mega, giga, tera, peta, exa, etc. And maybe you will learn who Karl Marx is. So this is so far the end of the introduction. Do you guys have any questions? If not, let me move on to the actual science in question. Well, for this week, I don't expect that you have read the first chapter, but I do expect you to actually look at the first chapter and read it. By Thursday's class, I expect you to ask questions. We'll talk about the concepts of energy. We'll later, tomorrow, actually on Thursday, talk about things like power. Later in the semester, we'll talk about concepts of momentum and other things. And these are words that you hear very often in your everyday life. You can watch a sporting event and hear announcers talking about how much energy is in the stadium, like on Sunday in Seattle, for example. If you watch hockey, like I do, if you sometimes notice that I speak with a Russian accent with a slight Canadian twang, there's a reason for that. I'll try to keep my boots short. So, I do watch ice hockey and I play. So, every team usually has the so-called energy line. Well, these are the guys who go out there and pound the other opposition. Like, again, a couple of days ago in Vancouver, there was a 5-on-5 brawl at the start of the game with Calgary, I think. So, you hear energy line, you hear energy in the stadium, you hear about energy drinks, you hear about energy supplements. You can buy 5-hour energy in little bottles, incidentally, which has no calories in it. Want to describe this concept, you fundamentally sort of know that energy is what takes to create motion. So, you need to apply force to start moving objects, but it, takes energy to generate that force. I had to eat breakfast this morning. If I didn't, I'd be grumpy, if I'm not usually. I have to expend some of that energy to start the ball swinging. If I'm about to walk into this bowling ball, please warn me. Of course, you also can see this concept in the fact that it takes energy to move things, and therefore there's energy stored in motion, and motion requires energy, and energy from motion can be converted in other means. That is known to you, both intuitively and from demonstrations. Let me show you this kind of to set you in the mood for what we'll be discussing on Thursday, the demonstration of how much energy can be stored in the motion. You've seen Armageddon, I assume. I guess you guys were, like 10 when it came out? Maybe less. Spectacular, typical Hollywood disaster movie. Now, let me ask. So first of all, I told you to listen carefully, to also look. Did any of you see anything strange? Yeah, in the back? The sound was traveling just as fast as the comet was. How did it sound? It sounds like a jet. It sounds like an airplane. It's sort of, how would a comet sound? Is comet a jet? Probably not. As far as we know, it has no engines. Also, the comets travel, comets travel with a very high velocity. Travel with the speed of 20, 30, sometimes more kilometers a second, which is above the speed of sound. And as it turns out, the principle that's behind the cracking of the whip is very similar to the principle of sonic boom. In fact, it is a sonic boom that you hear when you see a jet flying overhead, or when you hear a jet that's flying faster than the speed of sound in air. It produces a shock wave, produces a sonic boom. It doesn't sound like a regular jet. A comet flying with the velocity of 20 kilometers a second is not going to sound like a jet. It's just going to produce a very sharp crack. And probably by the time you hear about it, it would have hit, because it's traveling faster than the sound that it produces. That's one. Are there any other potential issues that you have observed? Yeah? The way the ground erupted, what's strange about it? It kind of blew up in segments. That's actually an interesting point. Let's look at it again. This actually isn't so bad. You know, if this comet landed in an ocean, how would it look? What would it produce? It produces a wave, maybe a tsunami. Waves don't necessarily travel only in water or air. Waves travel in solids as well. If I knock on a table, if you put your ear to the other end of the table, you hear vibrations. In fact, you hear them faster than when they travel in air. This is one of the ways you can actually listen to an incoming train. You can put your head on the rail and listen. Not something that I would suggest you do. Sound travel faster in solids than in gases. This is something that we'll discuss in a few weeks. So sound is an example of a wave. Earthquakes, as you know, travel in solids. Earthquakes travel on the surface. They also travel through the bulk. So what you will see is this eruption is actually a wave generated on the surface of the Earth from impact. It basically looks like a wave generated by a pebble that you may throw into a pond. And the only problem, of course, is that the wave speed, the wave velocity is very high. It's about 2 kilometers a second. So by the time this wave would have reached you, the observation point, which was, I guess, at Notre Dame, shouldn't have taken 3 or 4 seconds that the Hollywood inserted for dramatic effect. It would have taken about a second from impact to the place. You can look at the picture. There's Eiffel Tower, and it's sort of a mile away from the Notre Dame de Paris. So it would generally take about a second for that wave to propagate. But the propagation would be exactly like propagation of waves on the surface of the water, just a little bit more destructive because the ground isn't supposed generally to vibrate that much. It isn't as elastic as the surface of the water. Any other issues you want to discuss? You have seen the fireball, right? The entire explosion looked sort of like the nuclear explosions looks. There's a reason for that. Why does that happen? That actually is probably realistic as well. The reason this happens is that this mechanical motion from high velocity of the comet, from the energy stored in the motion of this heavenly body, is converted into other forms of energy on impact. And primarily it's converted into heat. This heat ignites a fireball. This heat heats up ground and air around the point of impact. Warm air rises up. We'll learn about that also, I think, in 2 weeks. And so you see the smoke and the debris rising up in the mushroom-like cloud, which is also what happens in the nuclear explosions. That part is probably also semi-realistic. So, you know, Hollywood knows how to make explosions work. The, you know, sound of a comet is a little bit made up. So, aside from this, what is energy? Again, we know how to talk about energy intuitively, and we generally associate energy with the ability to move objects. For example, you know that you need to fill up your car either with gasoline, or if you have a Nissan or a Ford, or if you can afford a Tesla, you need to fill up your car with electricity. So you need energy to propel things. You need energy to move your body parts. We need energy to warm up foods. We need energy to produce other forms of energy like electricity. And so we can talk about conversions of one type of energy to another, which we'll do in a second. But we can also define the energy in a little bit more fundamental way. There's a fundamental definition from Webster This isn't very helpful. It says a fundamental entity of nature that is transferred between parts of a system in the production of physical change within the system, and usually regarded as the capacity for doing the work. That's very helpful if you know what work is, so we need to define that too. Work is a measure, again, of an ability to apply force over some distance. So work and energy are often interchangeable quantities. So again, this definition tells you that energy in general is associated with an ability to make things move. And there's an alternative definition that is also often used. It's the ability to produce heat. And heat, you know, is sort of a form of energy you can actually feel. You can generate heat yourself. In fact, you do generate heat 24/7. I think Rich Moller also says this in the book, that you all guys are as bright as a light bulb. I'm not sure if it's a compliment. We'll have demonstrations of that. You all generate heat that can be seen by infrared imaging. You generate generally about 100 watts more radiation energy than you absorb from the environment. So literally, if you look at yourself through infrared goggles, through night vision goggles, you'll be as bright as a light bulb, like that one. Actually, in space, you'll generate much more. In space, your body will not absorb radiation from the environment, but you radiate close to 2 kilowatts of power. And so that's the reason why it gets kind of cold in space without a spacesuit. That's the reason why spacesuits have to be insulating. And that's also a reason why spacesuits are white. And again, we'll discuss radiation later on. So you can also generate heat by, rubbing your hands, right, if you're cold. So this is, again, an example of converting a mechanical motion into something you can sense as temperature increase or heat. And then there's a more philosophical, perhaps, definition that energy is a measure of the ability to turn order into disorder, or actually the other way around. We talk about energy as something is needed to drive the economy. That's a big question in society. And the main reason for this is that economy is an example of turning disorder into order, generally speaking. There are counterexamples, but usually, we have factories, plants, we have buildings that we build, which we assemble raw parts into structures that look more orderly than what we started with. All that requires energy. So energy is this universal currency in nature that is required in order to move things or in order to assemble things. We typically, in physics, describe it, again, more mathematically. We say that energy really is something that is additive. What it means is that if I, ate a croissant, I'm trying to make a French accent, that doesn't work. I had a coffee and a croissant for breakfast, so that gives me a little bit of energy, enough to survive this lecture. I will eat lunch a little bit later on. That will increase my energy level, hopefully. So energy is additive. The amount of calories you consume adds up throughout the day. If you continuously add energy to the object, it will continue to move faster. This is how pushing people on swings work. If I continue to add energy to this oscillating object, it will continue to move faster and faster until I subtract energy from it. So you can add energy, you can subtract by performing mechanical work or by applying forces. Energy also can be converted from one form to another. You can convert electricity or gas, natural gas energy, so chemical energy or electrical energy into heat. That's what we use to prepare food. You can convert chemical energy in the gasoline into mechanical motion of your automobile. We can convert sun radiation, solar energy, again, into electricity and later into other forms, etc. And the most fundamental, most important law in physics is the fact that all fundamental processes conserve energy. And so this energy conservation concept is the most fundamental in physics. And it's a little bit different from what you hear in the news when you hear that we all must conserve energy. Typically, we talk about saving. Typically, we talk about reducing consumption. In physics, we talk about energy conservation as the fundamental law that says that energy can be transferred from one set to another set, but the total usually remains the same. I'll get back to that in a second. We talk about three kinds. Fundamentally, although in everyday world, they may exhibit themselves as very different kinds of energy, but fundamentally, there are three kinds of energy. There's kinetic energy in motion, and so we associate kinetic energy with motion with the speed with which the motion moves. The larger the speed, the more energy is stored in this motion, and therefore the more energy we can extract from it. So the reason that the meteors and asteroids are so destructive is because the amount of energy stored in them depends on their velocity, and that velocity is high. That velocity is 20, 30 kilometers a second typically, which is larger than practically any other object on Earth except for artificial satellites or rockets that we launch. This energy also depends on the mass of the object. We'll talk about inertia a little bit later on. The mass is the measure of inertia. It's a measure of how difficult it is to make something move, but it also is a measure of how much energy is stored in the motion of the body. And so, in fact, by measuring the amount of destruction that asteroid, or it was a comet, I think it was an asteroid in Armageddon. So the amount of energy stored in an asteroid by amount of destruction, by observing how much destruction it imparted on Paris, we could have estimated, or we can estimate, how big the object was. I actually did that calculation once. The size is sort of roughly 1/4, about a quarter of this building. So it's a decent chunk of rock. So the larger the mass, the more kinetic energy. This bowling ball, has a lot of energy in it, so it can impart some destructive force if I were to try to stop it. The other type of energy is called potential. This is the energy that can be stored. And there are, again, several different types. The potential energy can be stored in the gravitational field. We can store energy in electrical devices. I'll turn it on, and I'll demonstrate. So here's an electrical device called a capacitor. It stores energy. The name capacitor roots from the word capacitance, or capacity to accumulate something. In this case, to accumulate electrical energy. So I can store electrical energy in this capacitor by connecting it to a source of electricity. This thing, it's a high voltage device. I have to be a little bit careful handling it. Don't want to touch electrodes unnecessarily. But I can demonstrate how much energy can be stored in this relatively small device. So I've charged this capacitor to the voltage of about 2,000 volts. Do you think it's large? We'll find out. If I discharge it quickly, you'll see how much energy is stored. So again, this energy stored can be now converted into other forms. You see a flash, so it can be converted into light. You heard a sound, so this energy was converted into mechanical. This thing smells now almost like gunpowder, so it was converted into some kind of a chemical energy, and the energy also could be converted into heat. And the last part that we'll discuss again on Thursday is so-called mass energy, and that has to do with the Einstein famous E = mc² equation. So let me stop here. We'll continue discussing energy and power on Thursday. And again, if you have any questions, come now, and we'll discuss other things on Thursday.